Hello and welcome to yet another video of Cornerstones of Math. Today's video is about one of the most famous applications of integral calculus, finding the length of a curve. We have three problems right here, each given with the curve defined by an equation and an interval. And we also have this nice difficulty gradient that the problems get progressively more difficult as we proceed. So let's get started. The formula for the length of the curve is very famous. The length L of a curve defined by the equation y equals fx, where x is from a to b, is the integral of the square root of 1 plus derivative y prime squared, where x is from a to b. So let's apply this formula to our three given problems. As for the first problem, the curve is y equals x times square root of x, where x is from 0 to 1. The equation can be also written as x to the power of 3 over 2, which gives the derivative 3 over 2 times x to the power of 1 over 2. So directly applying our formula for the length of the curve, the length L is given as integral from 0 to 1 square root of 1 plus the square of the derivative, hence 9 over 4 times x. This can be written as integral 1 plus 9 over 4x raised to the power of 1/2. This integral can be done by simply applying this very basic formula that you learned from calculus class. So we have first 1 plus 9 over 4x, and the power increases to 3 over 2, then 2 over 3 from this part, and then 4 over 9 from this part. So this and the endpoints 0 and 1. So we have 8 over 27 times now this part, and when x equals 1, we have 13 over 4 raised to the power of 3 over 2 minus, when x equals 0, we simply have 1 raised to the power of 3 over 2. So we have 8 over 27 times, we have 13 square root of 13 divided by 8 here, and 1 here, which can be written as 1 over 27 times 13 square root of 13 minus 8. Let's move on to the next problem. Now the curve is y equals 4 over 5 times 4th root of x to the power of 5, and the interval is from 0 to 1. Notice that we can write the function as 4 over 5 times x to the power of 5 over 4. Hence the derivative is 4 over 5, then 5 over 4 comes down, and x to the power of 5 over 4 minus 1, which gives x to the power of 1 over 4. Therefore, the length of the curve is integral from 0 to 1 square root of 1 plus, and the derivative squared is x to the power of 1/2. So we have to do this integral. There can be many ways, but here I am going to show you just one method. If you encounter an integral which contains radical functions like this, one method that works many times is just substitute the entire thing with another variable. For example, letting t as square root of 1 plus x to the power of 1/2. One advantage of this method is that the radical can be easily removed by simply squaring both sides, like t squared gives 1 plus x to the power of 1/2. So x to the power of 1/2 equals t squared minus 1, which gives x equals t squared minus 1 squared. Therefore, dx is given as 2 times t squared minus 1, then we must have 2t here times dt, hence 4t t squared minus 1 dt. Now when x equals 0, t equals 1, and when x equals 1, then t equals square root of 2. So we have integral now from 1 to square root of 2, and this is t, and dx is 4t, t squared minus 1 dt. So we have constant 4 integral, and we have t to the 4th power minus t squared. So we have 4 times the antiderivative, t to the 5th power over 5 minus t cubed over 3. Here, as for the first term, substituting square root of 2 gives 4 times square root of 2, and substituting 1 gives 1. So this divided by 5 minus, and the cubic part, which gives 2 square root of 2 minus 1. So if you simplify this, you will obtain 8 over 15 multiplied by square root of 2 plus 1. And the third problem, and we have some juicy one right here. This is the real deal. Here the function is y equals square root of x, and the x is from 1 over 12 to 1 over 5. It is well known that the derivative of square root of x is 1 over 2 times square root of x, hence the length L of the curve is integral. Now from 1 over 12 to 1 over 5, square root of 1 plus this squared, which gives 1 over 4x. So how do we carry out this integral? Will the same trick work? I mean, can we substitute the entire radical thing with t being square root of 1 plus 1 over 4x, just like we did in the previous problem? Well, let's try this. Then we have t squared is equal to 1 plus 1 over 4x. Hence 1 over 4x gives t squared minus 1. And if you solve for x, you will obtain 1 divided by 4 times t squared minus 1. Here we also need dx, which is given as 4 times t squared minus 1, now squared. And since the original power was negative 1, we also need minus sign here. And by the chain rule, we have 2t here. So we have minus t divided by 2t squared minus 1 squared dt. We also need 2 endpoints for our new variable t. When x equals 1 over 12, then t is square root of 1 plus, and the second term becomes 3, so we have 2. And when x equals 1 over 5, t equals square root of 1 plus, now the second term gives 5 over 4, which gives us the value 3 over 2. So we have integral from 2 to 3 over 2, this t, and this minus t divided by 2t squared minus 1 squared dt. Here, if we write 3 over 2 here and 2 here, then we can eliminate this minus sign. Then we have the integrand t times t divided by 2t squared minus 1 squared. Now some of you might ask, why didn't you combine the numerator part to write it as t squared? Well, that's because when integrating this function, we need to split the function anyway. And by splitting, I mean the famous integration by parts. Here, u must be the function that is easy to differentiate. Hence, we let this t as u. This gives u prime equals 1. This means that v prime is equal to t divided by 2t squared minus 1 squared, but v prime must be the function that is easy to integrate. So, is this function easy to integrate? Well, yes. Notice that t in the numerator appears if we differentiate t squared minus 1 in the denominator. So we can think of this v prime as a result of the power rule combined with the chain rule, and it is not that difficult to find out that the antiderivative v is given as minus 1 divided by, now 4 here, then t squared minus 1. So we have everything we need, and the result is First, we need uv part. So we have minus t divided by 4 times t squared minus 1 here, with 3 over 2 and 2, then minus integral. Now we need u prime v part, which is simply minus 1 over 4 times t squared minus 1. Substituting 2 gives negative 1 over 6, and substituting 3 over 2 gives negative 3 over 10, but since we have to subtract this value, we have plus sign here. As for the next part, some of you might have realized that we can easily integrate this 1 over t squared minus 1 part by applying this famous partial fraction formula. So now the sign becomes plus, then the constant part becomes 1 over 8, then integral of 1 over t minus 1 minus 1 over t plus 1. So these two gives 2 over 15, then plus 1 over 8 times. And the integrals of these are easy. They are just integrals that gives logarithmic functions. And you can easily find that the end result is just ln absolute value of t minus 1 divided by t plus 1. And you can easily find the answer 2 over 15 plus 1 over 8 times ln 5 over 3. Now, if you are interested, then go try this bonus problem as well. Here, the interval of integration is from 0 to 1, like the previous two problems. This should not be that difficult because I just did all the integrals for you. Also, I made a video on finding the length of the curve given by quadratic function, and I highly recommend checking out this video as well if you're interested in the topic. Thank you for watching, and I will see you in another video.